All right, for those of you on Zoom, please type something into the chat with regards to roll. I forgot to bring a piece of paper. There's only 5 of you guys. I'll figure it out towards the end of class. Okay, so today we have a couple of things to talk about. We have Pnp transistors to talk about, and then we are going to begin a long section of class regarding BJTs as amplifier circuits. So let me make sure nobody's asking any questions here. Everybody just saying here. All right. So let's start with the Pnp Bjt. All right. So in a Pnp Bjt, we have the following setup. Yes. Oh, I'm sorry. Okay, sorry. Don't know why this is not showing the right thing. All right, there we go. Sorry about that. We still have the sandwich structure as before. Okay. But now we will have a neutral P++ region, which is our emitter. And we put that at the top. So in a PNP transistor, the point of the highest potential in the circuit is usually the emitter. So we'll have some emitter current like this. Then we have a neutral N+ region serving as our base. And we're going to define our base current as flowing out towards the base terminal instead of flowing in. Sorry, this should be a B, not an E. And then finally, we have a lightly doped neutral P region at the bottom, commonly referred to as the collector. Here's our collector pin C, and here is our direction of collector current. Excuse me. And so our schematic representation of a Pnp Bjt usually looks something like this. Here's our emitter, IE. Here's our base, IB. And finally down here, here's our collector and our current, IC. And so we have a voltage here, VEB, a voltage here, VEC, and a voltage here, VBC. Let me rewrite this one because my pen's getting ugly. VEC. All right. So for a Pnp Bjt, we can develop another table just like we did previously for the NPN, letting us know what all the different relationship possibilities are that tell us in what mode the device is operating. So for PNP transistors, if we put our applied voltage here, our junction bias here, to the base emitter junction and the base collector junction. And then our mode over here. One, two, three, four. We'll get something like this. So when VE is greater than VB is greater than VC, the BE junction is forward biased. The BC junction, that should be reversed. Hold on just a second. Oh, maybe not. We get forward active. VE greater than VB less than VC. Forward, reverse. This is saturation operation. VE less than VB greater than VC. Gives us cutoff. And then VE less than VB less than VC gives us I feel very strongly that I copied down some of these values for the position of the junction biases incorrectly. So I may come back to this and reverse active. There we go. And the reason why I say that is because for cutoff, both of them should be reverse bias because that means there's no current flowing through. And for forward active, I think one of them should be reverse biased as well. So now that I'm looking at it, I think this table is hot garbage. I'm not sure how I managed to copy down multiple things wrong, but I did. So I'm going to put some big question marks right here because I may have screwed this up, just to be real clear here. But we can figure things out pretty easily. Actually, we can figure it out right now. So if we have a PNP transistor in the forward active region, let's talk about what's going on in the forward active region. Let's draw this in this way. All right, so over here on the left-hand side is going to be my emitter. All right. And in my emitter, it is a very highly doped, so P++ region of neutral semiconductor. This is our base. So this is an N+ region. And then this is, let me move that over a smidge, our N+ region. And then here is our collector, and that is an N region. Okay. So what we want to have happen in a PNP transistor is effectively the exact opposite as what we had happen in an NPN transistor. So we want our emitter to be the source for a whole bunch of holes. Okay. So we're going to bias this guy in such a way that we have holes moving towards the base and electrons being supplied by the base. This junction, so this is our base emitter junction, needs to be forward biased. So we want the large concentration of holes to be able to diffuse across that junction very easily and get into the base region. So if the base emitter junction is forward biased, so let's change this guy. And then this guy is reverse. Right, pen thingy. Aren't you behaving yourself today? Sorry. Let's see what happens. Technical difficulties pissing me off. All right. So in cutoff, they should both be reverse. In forward active, they should be the opposite of what they are in. Oh, dang it, hold on. Forward active, we have the base emitter junction is forward bias. That is reversed. In saturation, they're both forward. In cutoff, and then, so this is the one that goes backwards. All right. So we want the P side potential to be higher than that of the base. So we have a VEB here that is greater than 0. So that's what's forward biasing this junction. And that is going to cause the holes to be able to diffuse through pretty easily. So these are the diffused holes in blue here, the diffused holes that are coming from the emitter. A small portion of them will wind up recombining with electrons in the base. And then we need our base collector junction to be reverse biased in order to create that large electric field, which is going to sweep through those charge carriers. So that means that we need for reverse bias, the base needs to be at a higher potential than the collector. And obviously then VE is at a higher potential than VB, which is at a higher potential than VC. All right. So in our PNP junction, the amount of holes that get swept through from the emitter to the collector, so the amount of holes in the collector region is smaller than that of the amount of holes in the emitter region. So just so that we're clear on our currents directions, we have IE like so, IB, and then IC. So we can say that IE is equal to IB plus IC. So it's the exact same relationship that we had for NPN transistors. It's just all of the current directions are reversed because everything is dependent now on hole carrier transport as opposed to electron carrier transport. Since we have effectively the exact same situation as we had, except holes are in charge of everything, and we've seen that our polarities for all our voltages are exactly opposite what they were before, we can easily develop our large signal model. And so I'm going to draw it in what might seem like a funny way, but I'll explain it momentarily. Sorry, have it here. VEB over VT. And here is our collector. So this is our collector current. IC, it is the exact same thing as what we had for an NPN transistor, except we use the voltage VEB instead of the voltage VBE. Exact same equation, exact same relationship for IS and all that kind of jazz. This is our base current over here. It will still be IB is equal to 1 over beta, times IC. And then here is our emitter current, IE, as said previously, is simply equal to IB times IC. So our relationships are then IC is IS, EXP, VEB over VT, IB is 1 over beta, IS, EXP, VEB over VT, and IE is beta plus 1 over beta, IS, EXP, VEB over VT. Since we have our large signal model pulled up and all that jazz, what do you think is going to happen if we include the effect, the early effect to our large signal model? So in this case, the emitter collector voltage causes a change in the collector current. So for the NPN transistor, we modeled this by multiplying all of these currents effectively by a factor of 1 plus VCE over the early voltage VA. For the PNP transistor, we are going to multiply everything by a factor of 1 plus VEC over VA. We literally just change the order of the subscripts. That's it. So early effect, I might have to break down and buy a new Surface Pen. 1 plus VEC over VA. Gosh, that looks terrible. VC divided by VA would get multiplied by IC. And since IB is a proportion of IC, it carries through there and as well. So early effect is easy enough to handle with a PNP transistor. We just multiply by that common factor. All right, our small signal model. Oh, I don't think I mentioned why we traditionally draw it in this way. So it's effectively an inverted drawing of the large signal model for an NPN transistor. And that's because the emitter is typically at the higher potential and we draw the highest potential terminal towards the top to make things less confusing. Another thing that I may not have mentioned, so I guess I'll go back and do this just real quick. If we notice on the drawing here, the emitter is at the top. The arrow is still attached to the emitter, but now it's pointing in. For an NPN transistor, it was pointing out. Still attached to the emitter, just the change in the direction of that arrow tells us whether or not we're dealing with an NPN transistor if it's pointed out, or a PNP transistor if it's pointed in. So sorry, should have mentioned that previously. All right. Yes, so we worked a whole heck of a lot of problems that would be considered a common emitter amplifier topology in with the NPN transistors. There are common collector topologies where the collector isn't grounded per se, but it's at an AC ground, and we'll talk about that literally later on today. But yes, so in the most simplistic amplifier circuits that we'll be dealing with of the PNP variety, typically speaking, the collector is the one that's at ground. Yes. The emitter may have a resistor between it and the power supply voltage. Sorry, I take that back. I take that was, so typically speaking, we'll see it in a minute, but typically speaking, the emitter would be held at the power supply voltage, and then we would still place the resistor on the collector, but it will be between the collector and ground versus the collector and VCC. We'll draw one and work an example problem in a minute. I feel like I've just confused everybody. So let's take a peek at this small signal model here real quick. And so this is something, so in Prashana's notes, he has it drawn what I would consider wrong the way he's done it. And I think it's just because he has defined V pi. Yeah, he's just defined V pi backwards. So for the small signal model, where we have our emitter on top, Here's R pi, which is relating the change in collector current due to the change in the base emitter voltage. So it's still playing the exact same role as before. Here is our base terminal. GMV pi. This is our transconductance multiplied by V pi. And so V pi is still based on the base emitter voltage, not the emitter base voltage. So in the small signal model, let me go ahead and include the early effect out here. Here is R naught. The small signal model for a PNP transistor is literally identical to the small signal model for an NPN transistor in terms of how we define all of the voltages, as well as how we define the direction of the currents. So for the small signal model, our emitter current is flowing up. Our base current is flowing from the base to the emitter, and our collector current is flowing from the collector to the emitter. Our definitions for transconductance and R pi and R naught are all exactly the same. Okay. So there is no difference whatsoever between the small signal model of a PNP transistor and the small signal model of an NPN transistor. Just want to be very, very clear about. The way Prashana has drawn it has all of the currents flowing in the opposite direction, but all of the quantities are inherently negative, and to me that's confusing as shit. So I'm going to use the methodology that the book uses, and everything is exactly the same as in a PNP transistor. Or excuse me, NPN transistor. All right, so let's look at a couple of example problems utilizing PNP transistors that might help us a little bit here. So let's start with one under what I would call simple biasing conditions, meaning there's just voltage sources applied to things. We don't have to worry about resistors or anything like that too much. So let's say that we have the following circuit. We have a transistor here, Q1, transistor here, Q2. The base of Q1, we are applying a voltage of 1.7 volts. Here we have a voltage of 0.82 volts. We have a power supply voltage of positive 2 volts. And our ultimate goal here is to determine this current IX. And the information that we are provided is that IS is equal to 3, excuse me, IS1 is equal to 3, IS2 is equal to 6 times 10 to the minus 16 amps. So this guy should be pretty straightforward, okay? So our goal here is to determine the quantity Ix, which it should be pretty obvious is just going to be the sum of this collector current, which I'll call IC1, and this collector current, which I will call IC2. We know that in general, IC for a PNP transistor is IS times the exponential of VEB divided by VT, right? So exact same thing as an NPN transistor, we just transpose the subscripts. So just for the sake of argument, I am going to define a voltage here, positive polarity on my emitter terminal, negative polarity on my base terminal. So this is VEB1. And then here, positive polarity on emitter, negative polarity on base. This guy is VEB2. So if I can find VEB1 and VEB2, I should easily be able to determine IC1 and IC2 and then simply add those two results together. Seem like a reasonable approach. Anything wonky or tricky or confusing about approaching it in this way? Just very formulaic, using the ground rules of our exponential model. All right, so low-hanging fruit here, what's VEB2? 0.82 volts. It's literally given to us. That one's pretty easy. So we can determine that IC2 is going to be, all right, what's IS2 in this case? We're told that IS1 is equal to 3, IS2 is equal to 6 times 10 to the negative 16 amps. So what's IS2? 2 times 10 to the negative 16. Nothing real hard here, all right? Our thermal voltage, 0.026 volts. And I get 9.954 milliamps here. All right. That bit should be fairly straightforward. Now this next part is where your gut reaction from having dealt with NPN transistors for so long may bite you in the butt. What's VEB1? Okay, so you're absolutely right. It is not 2 volts because that would be the potential difference between the emitter and the collector. It's not 1.7 volts because that would be the potential difference between the base and the collector. It is the difference of those two. You're exactly right. So VEB1 should be 2 volts minus 1.7 volts. So what I thought would be the common mistake here would be most people would say, oh, well, that's the voltage applied at the base, so that's VBE or whatever, and get that confused with VEB, which is different, right? So because our emitter is tied not to ground, which is unusual for us, I feel like that's a pretty common mistake that people would make. So I just wanted to watch out for that. So good job catching it. So to reiterate, VEB1 is the same as VE minus VB 1, which is 2 volts minus 1.7 volts is 0.3 volts. From this, we have IC1 is equal to 6 times 10 to the minus 16 amps. EXP 0.3 divided by 0.026 is going to be equal to 61.552 picoamperes. So IX is equal to IC1 plus IC2 is approximately equal to IC2 of 9.954 milliamps. Because IC1 is several orders of magnitude smaller. Let's see what we got in the chat here. Just somebody else saying that they're here 38 minutes into class. Okay. Hopefully this guy fairly straightforward. Simple voltages used to bias things. It's really just kind of paying attention to the details. Anybody have any questions about this guy before we move on? All right. Then let's take a look at another guy. Slightly different situation. Looking at things from a slightly different perspective than we would normally do. All right. We have positive 1.5 volts applied to the emitter of our PNP transistor. B, E, C. I like to draw those just so I don't confuse myself. We are told that IS is equal to 8 times 10 to the minus 16 amps. And we want to know what value of beta places our transistor at the edge of saturation. So let's talk about what the edge of saturation conditions would be for a PNP transistor, right? So for an NPN transistor, the edge of saturation was defined as when the collector emitter voltage is the same as the base emitter voltage. For a PNP transistor, it's the exact same thing, except we transpose those subscripts. So the edge of saturation means that VEB is the same as VEC. I have a potential question here that I want to make sure, well, I was going to pose it as a question, but there's not a good way to answer it. I was going to ask, is there any way for us to know the voltage at the base just by looking at this thing? So that would be an intuitive guess, all right? So I can see why someone would think the voltage at the base pin itself would be 0 in this case. But with the base pin voltage being 0, that would imply that there's no voltage drop over that 100 kilo ohm resistor, which means there's no base current, which means there's no collector current, which means the transistor is off. So I can see easily why somebody would make that assumption, but we have to think about what's really going on here and what the implications of that are, right? We are trying to figure out what value of beta places this guy at the edge of saturation, meaning it should be somewhere between saturation and forward active region, which means that base voltage has to be non-zero. Specifically at the base needs to be non-zero, okay? So it's those kinds of little intricacies that are going to tend to trip people up a whole heck of a lot when they're dealing with PNP transistors, and when we get into more difficult bias circuits, which are what we're going to be talking about on Monday. All right, so I am going to draw my large signal model because for me, I felt that this helps me out when looking at this circuit. So I have 1.5 volts here at my emitter terminal. Here is my voltage VEB. Here's my base current. IB is equal to 1 over beta times IC. There's base terminal. Here's the collector terminal. Here's my collector current. Here's my emitter current. All right, so between the collector and ground, I have this 1 kilo ohm resistor. And between the base and ground, I have this 100 kilo ohm resistor. All right. Another way to look at this between my emitter and this ground is like me having a 1.5 volt source, and I could do the same thing over here. Right, between those 2 points, I have a known potential of 1.5 volts. Because this 1.5 volts up at the top of our circuit here is a voltage with respect to ground. I'm drawing it that way because it helps me do my Kirchhoff's voltage law loops when I think about it in a circuits one perspective where I literally have a loop to do KVL around. So that's just me kind of helping myself out. All right, so at the edge of saturation, we know that VEC, VEC is equal to VEB. So I can do Kirchhoff's voltage law around the left-hand loop and the right-hand loop and get a couple of equations. Around the left-hand loop, so KVL at left-hand loop, I get VCC 1.5 volts is equal to VEB plus IB times RB, or I'll be explicit here. I'm calling this guy RB and this guy RC, which I could write as VEB plus 1 over beta IC RB. So everybody okay with this equation? I'm simply saying that the 1.5 volt drop is equal to the voltage drop over that diode, which has a voltage drop of VEB, added to the voltage drop over that 100 kilo ohm resistor, which is IB times that resistor value, and I'm expressing IB in terms of my collector current, IC. If I do Kirchhoff's voltage law around the right-hand loop, what am I going to get? Anybody care to venture a guess? So let me ask a question. What's the voltage drop over that dependent current source? That's the hard part of this. Any thoughts?
1.5 minus the voltage drop.
I do to an extent, and so let me explain what I mean by that. What's the nodal voltage at the top terminal? VE. Okay. So which is 1.5 volts for sure. But then the voltage here at the other terminal, or excuse me, at the other terminal is simply VC. So it's VEC, which we know is exactly the same as VEB because this guy is on the edge of saturation. All right. So VCC, KVL around my right-hand loop, excuse me, gives me VEB plus IC times RC. Which I can rewrite. Actually, I don't even need to rewrite it from there. Turn that off. So I now have these two expressions, a KVL loop around the left-hand side, a KVL loop around the right-hand side, and have found that VCC is equal to both of these quantities. So I can simply set them equal to each other, right? So if I do that, what I get is VEB plus ICRC is equal to VEB plus 1 over beta times ICRB. I can subtract VEB from both sides, which gives me IC times RC is equal to 1 over beta IC times RB, excuse me, where there's a common factor of IC on both sides, finally yielding beta is simply RB over RC, which is 100 kilo ohms divided by 1. Why is it writing so terribly? 100 kilo ohms divided by 1 kilo ohm gives us beta is equal to 100. So with beta at a value of 100, this guy is on the edge of the saturation range. Anything wild or crazy there? Really, not so much. But to me, the hardest part was realizing the voltage drop over the dependent current source, which we're kind of been drilled into our heads through so much simple circuit analysis that the voltage drop over a current source isn't related to the current flowing through the current source, really. We had an alternate route here because we know that we're on the edge of saturation. Okay, so, all right. Let's take a look at one last problem here. We have another Pnp transistor. Here's V out. Here's 2.5 volts. Emitter, base, collector, 2 kilo ohms. This guy right here is RC. Let's see, we're told that IS is equal to 3 times 10 to the negative 17 amps. Beta is equal to 100, and our early voltage is equal to infinity. And really, on this particular problem, I would argue it doesn't matter what the early voltage is. And the reason why I say that is because VEB is equal to VEC by definition, which means it's always on the edge of saturation. So the early effect shouldn't come into play because it's not deep into forward active region or anything like that. We want to determine two things: the output voltage and our small signal voltage gain. So in this problem, I found it useful to draw the large signal model of our system. So here's my emitter where I have 2.5 volts applied. I don't know why my pen is not putting lines where I draw them. All right, so between my collector and ground, there is a 2 kilo ohm resistor. And this is my voltage, V out. And then between my base and my collector, I have a short circuit. So how am I going to figure out V out? Let's start there. What's the intuitively obvious way that we're going to wind up figuring out V out? I don't need any equation. Just kind of tell me what we're going to do. Find the current flowing through RC, multiply it by that resistor value, and we're good to go. So good old Ohm's law, right? So V out we know is going to be 2 kilo ohms times the current flowing through that resistor. So that begs the question of what is that current flowing through that resistor going to be in terms of our collector current, IC. So it will absolutely be the exact same current as IE in this case, right? So IE, which we could write as IB plus IC, which is the same as 2 kilo ohms times 1 plus 1 over beta IC. So the reason why it is the exact same current as the emitter current is because the current flowing here is IB. And so if we do KCL at the node, at node C for the collector, we have the collector current IC flowing down into the node and the base current IB flowing to the right into the node. And those two guys must add together and then flow down through that 2 kilo ohm resistor. So very good catch. All right. So how are we going to figure out what IC is or what VEB is? Because if we know one of those, we can get the other.
Create a second equation.
What are your thoughts on the second equation there?
2.5
Okay, so you're suggesting we do Kirchhoff's voltage law around this guy. Well, that's exactly how I did it as well. So we can say that 2.5 volts, our power supply voltage, is equal to VEB, which we don't know, plus V out, which we don't know. But since V out can be expressed in terms of IC, we've already done that part. We can say that it's 2 kilo ohms, 1 plus 1 over beta. IC in terms of VEB is IS, EXP, VEB over VT. And now we have one equation, one unknown that we can solve. So solving this guy gives us VEB is equal to 805.016 millivolts, which in turn gives us a collector current of 839.101 microamps. So we figured out, or we haven't yet figured out what V out is then, right? So now that we know what IC is, we can figure out V out pretty easily, which it looks like I didn't bother to do. So I'll have to get out my calculator here. That's going to be simply 2 kilo ohms, 1 plus 1 over beta is 1.01. 839.101 microamps. $1.695 volts. So that is V out, okay? All right. The second part of this question, we are asked to determine the voltage gain of our system. The voltage gain is based on the small signal parameters of our system. So we would need to know our transconductance. GM by definition is IC over VT. So in this case, that gives us 32.273 millisiemens. Our pi is beta over GM, gives us 3.098 kiloohms. Our small signal model for this guy B pi. B E C 2 kiloohms. R out, or excuse me, V out is still the voltage drop over there. V let's see, actually, hold on. So the base and the collector are shorted like so. Right. The emitter is AC grounded or small signal grounded. Yeah. So okay, so I made a dumb mistake on this when I was working it out because I haven't specified where an input voltage or anything like that would go, so it's really hard to figure out where the small signal voltage gain would be. I worked it in a dumb way, so let's forget part C of this question. We've developed the small signal model, so that's good enough for me. Let's forget that. Just develop the model. Okay, that's a dumb mistake on my part. So it's 9:05. I actually have, I think, 6 more pages of notes that I was hoping to cover today, all on BJT amplifier circuits, but it looks like that's going to have to get put off until Monday. So I guess we're going to knock off about 10 minutes early. I apologize for my disorganization today. I don't know, to me, it was a shitty lecture, whatever. Messed up the table at the beginning and then had an example problem that I made a mistake on. So to me, it's a bad lecture, whatever. All right, so see if there's somebody agreeing with me. We have classes Monday. We do not have classes Monday. Monday is the Martin Luther King Jr. holiday. We have classes next Wednesday. So I apologize if I said anything about what we'll be doing on Monday. On next Wednesday, we will get into chapter 5, which is BJT amplifiers. My goal on Monday is to introduce the 3 common amplifier topologies, and then we're going to talk about calculating input and output resistances for those amplifier topologies. And if we have any time, go over some biasing schematics. And then we're going to spend a couple of weeks really getting into granular detail about the different amplifier topologies, because you can make small changes based on what bias circuits you use that vastly change what the input and output resistances are, which then change what the voltage gain of the overall system is. So we need to look at things and kind of develop a shorthand notation for looking at these circuits, because as you'll see on Monday, if we do it the formal way, which is a test source method every time, we're going to get bogged down real quick. So what we're going to start working on next Wednesday is how to qualitatively analyze BJT circuits, which is qualitatively analyzing any transistor circuit is usually the way that most textbooks handle things after the first little introduction section, because if you went through and quantitatively worried about every little thing, it takes you 3 hours to work every damn problem. So we're going to look at some kind of fundamental building blocks and make some observations that will vastly speed up our circuit analysis instead of starting from scratch every single time. All right. So I will see you guys on Wednesday. For those of you that are here, use the back of this sheet. Somebody, oh, you already made one? Thank you, Jack. All right, see you guys on Wednesday.